In this lesson, we're going to talk about related rate applications. And in calculus, related rate applications involve finding a rate in which one quantity changes by relating that quantity to other quantities whose rates we know. So we use the idea of the derivative to find the rates of changes of these quantities, and then we plug in the values that we know, and then we can solve for the unknown quantity that's changing that we're looking for. And so there's a nice problem-solving strategy here laid out for us. In the first step, you're going to figure out what all the variables are and label them. So, for example, if we're talking about volumes, we're going to want to assign V for volume. And then after we figure out what all the variables are, it's really helpful if you can draw a picture to do that, because it really helps you think through the problem. Okay, the next step is you want to state in terms of the variables the information that's given and the rate that you need to determine. So this is where you read the problem carefully and you list what you know, what you're looking for in terms of the variables that you defined in step 1. In step 3, it says find an equation relating the variables introduced in step 1. So if you're talking about the volume of the sphere, which is what our first example is going to be, then you want to find the equation or the formula for the equation of a sphere. Step 4 is you're going to take the derivative of both sides. You're going to end up using the chain rule along with other methods that we've learned to take the derivative. And then the last step is you substitute all the known values into the equation that you have so that you can solve for the unknown. So let's read this first example. We have a spherical balloon is being filled with air at a constant rate of 2 centimeters cubed per second. We need to figure out how fast the radius is increasing when the radius is 3 centimeters. So in step 1, we need to find and figure out what all the variables are. So we have the volume of a sphere. We're going to call that V. We have the radius. We're going to call that R. Then we have the change in volume. That's going to be the derivative of the volume with respect to time. So that's going to be dV dt, which you can also write as the derivative of V. But you have to keep in mind that the derivative is with respect to time. And then the change in the radius. Which is the derivative of the radius with respect to time, which we'll call that dr dt, or you can write it as r prime. Okay, the second step says state in terms of the variables the information that's given and the rate to be determined. So if we look at the information that's given, we're given the change of volume, which is 2 centimeters cubed per second. So we know that the derivative of the volume with respect to time, which we can also write as v prime, that is 2 centimeters cubed per second. We also know that the information that we're looking for is when the radius is 3 centimeters. So we can put down that the radius is 3 centimeters. And what we're looking for says we're looking for the change in the radius, how it's increasing. So this is what we're looking for, dr dt, or r prime. That's the unknown that we're trying to find. Okay, step 3 says we're going to find an equation relating the variables in step 1. So the equation that we're dealing with in this example is going to be the volume of a sphere. And this is where it's really handy to have those reference sheets that I posted on Canvas for you, because it has a lot of formulas, especially geometric formulas listed on there. So the volume of a sphere is going to be V is equal to 4/3 pi r cubed. Step 4 is to find the derivative. So I'm going to take the derivative of both sides. Now remember, v is changing and r is changing. So v and r are functions. So when I take the derivative of v, that's going to be dv dt. 4/3 pi is a constant. So when I take the derivative of r cubed, I got to bring that 3 down in front. So I'm going to take 3 times 4/3, which will end up with just 4 pi r. And then I have to take the 3 and decrease it by 1. Now, because of the chain rule, remember r is a function of time because r is changing. So now I have to multiply it by the derivative of r with respect to t because of the chain rule. Because r itself is a function of time. So think of r as an inner function. Now, step 5 is you just substitute all the information in that you have and you solve for what you're trying to find. So since we're trying to find the rate of change of the radius with respect to time, this is what we want to solve for. And we're going to plug in all the other information. If we look back up in step 2, we knew that the volume changing with respect to time is 2 centimeters. Whoops, I think I made a mistake here. Let me rewrite that. It's 2 centimeters per second. So I'm going to plug in 2 for dv dt. The radius at the time that we're looking for is 3, so I'm going to plug in 3. And this is times dr dt, which is what we're trying to solve for. So when I take the 4 times the 9, because that 3 squared is 9, that's going to give me 9 times 4, which is 36. So that's going to be 2 is equal to 36 pi times dr dt. And when we divide both sides by 36 pi, that gives me 2 over 36 pi is dr dt. And then we can simplify that as 1 over 18 pi. And because the units of this is for the rate and change of the radius with respect to time, this is going to be 1 over 18 pi centimeters per second. So when the radius is 3, the radius is changing at a rate of 1 over 18 pi centimeters per second. Next example is an example of an airplane flying at a constant elevation. It says an airplane is flying overhead at a constant elevation of 4,000 feet. So when they say it's a constant elevation of 4,000 feet, we have to keep in mind that means it's not changing. So the height off the ground is staying the same at 4,000 feet. And there's a man that's viewing the plane from a position of 3,000 feet from the base of a radio tower. When the airplane is flying horizontally away from the man, the plane is flying at a rate of 600 feet per second. At what rate is the distance between the man and the plane increasing when the plane passes over the radio tower? So the first step is to draw a picture and identify the variables. Now, this picture I got from the book, it's a much better drawing than what I could have done. So according to the book, they're labeling the distance between the man and the radio tower, which is the horizontal distance from the man to the plane. They're labeling that as X. Let's see, what else? And then S is the distance from the man to the plane, the direct distance. We don't need to introduce a variable for this leg of the triangle right here because that is not going to change. It's going to remain at a constant 4,000 feet. The object's height above the ground is measured as the shortest distance between the object and the ground. The line segment of length 4,000 is perpendicular to the line segment of the distance between the man and the tower. So we're going to assume that this is the right triangle. Now, that's step 1. Step 2 is to identify what's changing in the problem, what we need to know, in what we're given in terms of the variables that we defined. So we're going to use the variables that are in this picture. So since x represents the horizontal distance from the man to the plane, dx dt is the change in the horizontal distance, which is the speed of the airplane. If we're looking at how this distance is changing from here to here, that's the speed of the airplane. Now, we were also told that the speed of the plane is 600 feet per second. So we can actually write down that dx dt is 600, and that was feet per second. What was asked for us to find is the rate of change in the distance between the man and the plane, that direct distance. So we're looking to find ds dt. Now it says that it also wants us to find ds dt when the distance of x is actually 3,000 feet. So we're also given that x is 3,000 feet. So this is step 2, identifying the variables that we have, the variables that have known values that we plug in, and then identify what we're trying to find. Step 3 is to actually come up with some kind of equation that incorporates all of these variables into some kind of formula so we can take the derivative. So since we're looking at a triangle here, we can use Pythagorean theorem. We can say that x squared plus 4,000 squared is equal to s squared. Now keep in mind that s and x, and I'll highlight it, these are functions of time. So when we do take the derivative, we're going to have to use the chain rule. Now we left it as 4,000 because that's just a constant. That does not change. Now the next step, step 4, is to take the derivative. So I'm going to take the derivative of x squared, which gives me 2x, and then times dx dt using the chain rule. When I take the derivative of 4,000 squared, that's just a constant, so that becomes 0. And then I have is equal to 2s times ds dt, because s is also considered like an inner function because it's changing with respect to time. Now I can simplify this by getting rid of the 2's on each side. And now I can rewrite it as x dx over dt is equal to s ds dt. So let's plug in all the information we know. We know that x is 3,000, so I'm going to plug in 3,000. We know that dx dt is 600 feet per second. We know that because it was given to us. Is equal to s times ds dt. Now here's the thing, we're looking for ds dt, so I'm going to highlight this. In order to find ds dt, I need to plug in a value for s as well. Now the information wasn't given to us directly in the problem what the value of s was, but we can figure it out. Since s is just the hypotenuse of a triangle, if I have a triangle, this side is always 4,000. And at the moment that we are trying to find this value for, we know that the value of x is 3,000. And so we can use Pythagorean theorem to find the hypotenuse, which is our value of s. So when I do 3,000 squared plus 4,000 squared is equal to s squared, and I solve for s, I'm going to get 5,000. So even though that information wasn't directly given to us in the problem, we had enough information to figure it out ourselves. Okay, so now I can replace s with 5,000 because I know when x is 3,000, s is 5,000. So now when I solve for ds dt, I'm going to multiply the 3,000 and the 600 on the left-hand side, And then I'm going to divide both sides by 5,000 to solve for ds dt. And when I do that, I get 360 feet per second. So what this is telling me is when x is 3,000 feet, s is 5,000 feet, and the way that this distance is changing between the man and the plane is it's changing at 360 feet per second. In this example, we're going to talk about a rocket launch. And it says a rocket is launched so that it rises vertically, and a camera is positioned 5,000 feet from the launch pad. Now, because it says the camera is positioned 5,000 feet from the launch pad, this 5,000 feet is not going to change. It's going to be constant. Now, when the rocket is 1,000 feet above the launch pad, its velocity is 600 feet per second. Find the necessary rate of change of the camera's angle as a function of time so that the camera can stay focused on the rocket. So we want to make sure that this angle, we find the rate of change of this angle, because as this rocket goes up, this angle is going to have to open up so it can keep track of how that rocket is going up and be able to get video of that. So we're trying to find the rate of change of that angle. So again, I got this picture, I copied it from the textbook, and the textbook labels h, which is the distance of the rocket off the ground, and then the 5,000 feet is constant, and then the angle is the angle of elevation looking up at the rocket. So in step 2, we need to identify our variables of what we have and what we need. So in the problem, it tells us that when the rocket is 1,000 feet above the launch pad, so we know that h is 1,000, then the derivative of h with respect to t, that's the change in height in terms of time, that's the velocity, that's going to be 600 feet per second. Now, the question is asking us to find the change in the angle with respect to time. So this is what we're trying to find. So in the next step, we have to come up with some kind of equation that relates all of these variables. Now, if you think back to trig, if I use the tangent of theta that's opposite over adjacent, we can set up h over 5,000. So here's our equation that relates the angle and the change in height. 5,000 is our constant, so we can just put that in there. If I solve this for h, I got h is equal to 5,000 times tangent theta. This just makes it a little bit easier. We don't have to do that, but it makes it easier when we take the derivative. So now let's take the derivative. So when I take the derivative of h, I'm going to get dh dt, because remember, height is changing with respect to time. So height is like an inner function. And when I take the derivative of 5,000 tangent, I'm going to get 5,000 secant squared theta. And because theta is also changing with respect to time, I have to use the chain rule and take times the derivative of theta with respect to time. So we know when dh dt is 600 feet per second. So I'm going to plug that in. We also have 5,000 times secant squared. Now this is an unknown right now, the secant squared. So I'm going to leave that blank for a second. And times d theta dt. So the d theta dt, that's what we're trying to solve for. So I'm missing a piece of information that I need to put in there for secant squared theta. so that I can finish solving this. And although they don't directly give us the information, we can find it using our triangle. So if we have our triangle, and we know that we're talking about when the height is 1,000, and we know that the 5,000 is a constant value, we can use Pythagorean theorem to figure out the hypotenuse, which would give us 1,000 square root of 26. So now, if we're looking at this angle, I can figure out what secant is. Secant is hypotenuse over adjacent, which would be 1,000 square root of 26 over 5,000. So I can now put that in for secant here. So secant of theta is 1,000 square root of 26 over 5,000. And I need to square that because it says it's secant squared. I'm going to take that 5,000 times the value that we just found for secant and square it. And then I'm going to divide both sides by that value to solve for d theta dt. Now, when I do that, I'm going to get that d theta dt is going to be 3 over 26. And because we're talking about the change in the angle, this is going to be radians per second. So in this last example of the section, we're going to talk about water draining from a funnel. It says water is draining from the bottom of a cone-shaped funnel at the rate of 0.03 feet per second. The height of the funnel is 2 feet, and the radius at the top of the funnel is 1 foot. And at what rate is the height of the water in the funnel changing when the height of the water is 1/2 foot? So you can see from the picture that I got from the textbook, the variables that are changing, those are already labeled for us. So when we go to step 2, we need to figure out the variables that we know and the variables that we need to determine. And the question is asking us to find the rate of the height. So that's going to be dH dt. It's the rate of the height with respect to time. And this is when the height is 1/2 foot. So we know that h is 1/2. We also are given the rate in which the volume is changing. So that's dV dt. That was changing at a rate of 0.03 feet cubed per second. And because it's draining, we should probably put a negative in front here because it's decreasing. All right, so we've recognized our variables here. Now let's determine an equation. So if you look up on that reference sheet that I gave you, you should find the volume of a cone to be 1/3 pi r squared h. Now, if you notice, the ratio of the sides in the two triangles are the same, so the ratio from r to h is 1/2, or you could write it as r is equal to h over 2. So I'm going to replace r with h over 2, so we can have everything in terms of h. Now, when we simplify this, I'm going to get 1/3 pi, and I have h squared times h. That gives me h to the 3rd. And then in the denominator, I square that 2, so I get a 4. And then I can continue to simplify this. If I multiply the denominators of 3 and 4, I can have pi h to the 3rd over 12. So now we have a formula that involves volume and height, and we have the information for that. So let's go ahead and take the derivative. So I'm going to take the derivative of the volume. Actually, let me write this out a little bit better first. We found that the volume is pi h to the 3rd over 12 with a little bit of manipulation. Now let's take the derivative. So when I take the derivative of v, I get dv dt. When I take the derivative of pi over 12 times h to the third, I get pi over 12 times 3 h squared, because I bring the 3 down in front, and then I decrease my exponent of h by 1. And then I still have to multiply that by dh dt, because we remember that h is changing with respect to time as well. So I've got dv dt is equal to pi over 4 h squared dh dt. So now I'm going to plug in that the height is given to us as a half. dv dt is decreasing at a rate of 0.03, and I have dh dt. So we are trying to solve for dh dt, so I'm going to divide both sides of the equation by pi over 4 times 1/2 squared. And so when we do that, we're going to get dh dt is negative 0.153 feet per second. So that is the rate in which the water in the funnel is changing when the height of the actual water is 1/2 foot.